Okay, folks, welcome back to another video. This one is going to be a little bit on exponential properties and a little bit of vocab. So we're going to introduce some new words, draw them to some math, and hopefully get at some meaning. Right? That's always the goal. Let's hop in. Okay, so the first thing I wanted to do was talk a little bit more about this thing e. So in the last video we saw I drew a function x of t or f of t, whatever it is, a function that I say is an exponential decay, has something like a constant out front times e to the something. So in the last video, I called it ct. I'm going to change notation a little bit on us here, and I'm actually going to call that c, I'm going to call it negative lambda. So this is this is going to be a notation that I use when talking about decays. Negative lambda t. Okay, so to transcribe something from the previous lecture, c is just going to move to negative lambda. C is negative lambda. All right, still just a constant. I'm just switching the name for that constant. So what I'm zoning in on right now, or honing in on right now, is e. E is called Euler's constant. It's just a number. So it is just a number. E is approximately 2.178. There's many ways that you can get to E. So many areas of math get there. You can get it as the solution to a certain kind of series, which is just a bunch of numbers added together. You can find it in finance as the limit of basically the limit of compound interest as you take the time between compounding interests to zero. So that's all I'll say about that, I guess. Feel free to look it up. And one other thing I wanted to mention, you're not going to be tested on this, but this is called some people have called this the most beautiful formula in mathematics. It's that e to the I pi is equal to -1. So again, you're not going to be tested on this. I just think it's a cool thing. I wanted to maybe perk up some mathematical heads here. It's kind of a crazy formula, right? I've got the exponential, just some number, raised to the imaginary, what? Times a pi? And it somehow equals -1? What's up with that, dude? It's crazy, but turns out to be true. You can prove it rigorously. Okay, so again, just a little piece of fun math trivia for you there. Okay, so that's what e is. E is just some number. So when I raise something, when I raise e to a power, it's just like raising any other number to a power. So like if I say 2 to the 2, that's just 4, right? 2 to the 5 is, oh god, 2 times 2 times 2 gets me 8, times 2 gets me 16, times 2 gets me 32, and so on. So similarly, if I do something like e to the 2, well, that's just basically 2.7 to the 2. That's around 7.4. And if I do e to the 5, that's just like, calculator, that's just 148. Okay, so roughly. So e is just a number. It acts like any other number. There's nothing particularly special about the exponential function. It's just a number being raised to a power. Notice that here our power is the thing that's changing in time. All right. I'm going to pivot a little bit. I want to talk about half-life and rate parameter. So if I've got an exponential decay, let me draw a graph for it real quick. So say that I've got an exponential decay, and I'm decaying from some high value to some lower value. I'm going to call this one, I'm going to call it a plus b up here. And we're going to decay down to b. Okay. So a decay might look like this. Boom. Okay. We're just going to decay to this asymptote at b. So I'm going to draw in a little dashed line here at b to indicate an asymptote. What the half-life describes, let's first mark our axes. This is x, this is t. What the half-life describes is the length of time it takes for me to cross half the interval from my initial value to my asymptotic value. So a point in between would be maybe right here. I'm going to call this b plus a over 2. I'm halfway. If I draw my line over and drop it down, Okay? This value is what I would call the half-life. It is the amount of time it takes for my decay to go from halfway to its total decrease. So half of the total change from where it is now. Now, similarly, if I step forward another half-life in time, if I step forward another half-life, I will have decayed another half. So I'm now 75% of the way to my asymptote. And if I take another half-life forward in time, t1/2 again. So, oh, sorry, this is actually 2 times t1/2 here. Pardon me. And this is 3 times t1/2. That's 3 times the half-life. Now I've gone 87.5% of the way to my final location. So this is 50% complete. This is 75% complete. Half of 50 plus 50 makes 75%. Then this is going to be 87.5% complete, and so on. So the change from each, like the change in percentage, is going to be 50% here, 25% of the original total, and 12.5%, and so on. It might be useful just to take a look at this, kind of familiarize yourself with the idea of half-life. So after each half-life, I go halfway from where I am currently to the goal, to the asymptote. Now I've drawn this little graph. I want to provide the formula, a formula that I might use to describe this. So the formula that describes this graph is a decay. It's slightly modified from our original version of decay because I got an additive constant. I'm ending up not at 0. So I would describe this as follows. I'd say x of t is b, that's the constant, plus an exponential decay. So it's going to be a times e to the negative lambda times t. We're going to talk about lambda here next. Okay, so let's talk about lambda. Lambda I call the rate parameter. Rate parameter. Checking on time, we're about 6 minutes in. Rate parameter. Oof, let's spell it appropriately. Parameter. Okay, so some intuition about lambda in the context of a decay. If lambda is large, the decay is fast. If lambda is small, the decay is slow. So the larger lambda, the faster my decay happens. The faster I end up really close to my asymptote. There's another thing I'll talk about, which is the inverse of lambda. So tau is the inverse of lambda. I'm going to call this thing my time constant. Time constant. Now, time constant also tells me roughly how long it takes for the system to decrease by a certain amount. So the half-life, just to draw a little analogy here, t1/2 tells me how much time it takes to lose 50%. Tau, the time constant, tells me how much time it takes to lose around 63%. So it's 1 minus 1 over e times 100%. That's how I calculate that number. So I'm dropping by something related to e. So tau takes me how long it takes to lose around 63%. It has units of time, typically. That's why I call it the time constant. Okay. So I've introduced these 3 things: rate parameter, time constant, half-life. That's it. They're all related to one another. So I'm going to try to show how they're related to one another. For one, here's an easy one. Tau is just 1 over rate parameter. So the time constant is 1 over the rate parameter. What I want to do is draw the relationship between the time constant and t1/2. So what is the relationship between t1/2 and the time constant? And we'll see why this is useful in just a moment, but bear with me while I solve this out. Another way of phrasing this question is to ask, at what time, hang on, at what time does uh, my decay function equal b plus a over 2? So I'll show why that's the same question here in a moment. But just to build some intuition before we hop in, if I know the time where this decay is at half the distance between its initial value and its final value, that tells me what t1 half is. So let's try that out. So what I'm going to do is I'm going to set the right side of my equation, or the left side of my equation, sorry. I'm going to set this side equal to b plus a over 2, and I'm going to solve for time. So b plus a over 2, that's my x at t1 half. X at t1 half. There we go. This thing is going to equal b plus a to the exponent of negative lambda times t1 half. So I've plugged in t1 half. It's a value now. It's no longer a variable. And then I solve for t1 half. So I'm going to cancel out the b's. I find that a over 2 equals a e to the negative lambda t1 half. All right. 1 half equals e to the negative lambda t1 half. There we go. Okay. And to invert an exponent, I just do a log. So I can do a natural logarithm, natural log on both sides. Natural log of 1 half is negative lambda t1 half. And there's a property of the logs, which is that natural log of a is equal to negative natural log 1 over a. So if I invert this log, I get a negative natural log 2 equals negative lambda t1 half, which means t1 half, we're almost there. T1 half, the half-life time, is natural log 2 over lambda. Or, because lambda is the inverse of tau, the time constant, this is just tau times natural log of 2. Notice that this means, since natural log of 2 is around 0.7, this means that the half-life is always shorter than the time constant. Okay. I can also mark the time constant on this same exponential curve. So let me go ahead and I'm going to mark all of these in blue. There we go. This is going to correspond to 1 tau life, 1 time constant passing by. Let's see. Here's 2 tau lives passing by. Boom. And so on. I think that's all I really want to say about for rate parameter, half-life, and the time constant. So this is the relationship between, here we go, between half-life, lambda, and tau, the time constant. That describes all of their relationships to one another. Okay, if I have a longer half-life, that means that I have a smaller lambda, a smaller rate parameter. It takes longer to decay. And it means I have a larger tau. I have a larger time constant. I want to launch now briefly into a few properties of exponentials. So the first thing that I want to mention is that the derivative of an exponential maintains its rate. So if you remember from calculus, the derivative with respect to time of some exponential function is just that exponential function with the argument, the rate parameter, brought down. So like it's going to be negative a lambda e to the negative lambda t. There we go. So the rate parameter stays the same up here. This is unchanged. So taking derivatives doesn't change anything inside my exponent. That'll be important in DL. Another thing I want to mention is that a derivative alone, an exponential alone always goes to either 0 or infinity. I mentioned this briefly in the last video. But an exponential alone, if there's no additive constant in front, will either decay to 0 or go off to infinity, depending on if the rate parameter, if lambda is negative or positive. So here we're choosing lambda always to be a positive number. Lambda itself is always positive, so we always get decays. If we have an overall positive value in the exponent, so if we had lambda negative, the two negatives would cancel, we would get growth, exponential growth. We use the word decay anytime lambda is positive. Lambda greater than 0 implies decay. So regardless of if we decay to 0 or decay up to some positive number, it's still called decay. There's also the case of what I might call inverse decay or decaying upward. So when I decay upward, I start at a lower value. I've got some asymptote up here, and I decay up to it. We'll talk about the mathematical form of this in the next video. So up next, we'll talk about exponential decay in fluid systems and exponential decay in electrical systems. So this will be the real meat and potatoes coming up next. We'll lay out some problems and go through them. In the final lecture, we'll talk through some intuition builders and start actually applying all this theory we've been building. Thanks, folks. I'll see you in the next video.